Okay, good afternoon. Let's get started. Lecture number 5, chemical admixtures. Okay. So in lecture number 4 last week, we discussed so-called mineral admixtures, right? Such as flash, silica film, slag. Okay. So chemical admixtures is kind of similar but different from what we discussed last time. Okay. Definition. Materials other than water, aggregate, hydraulic cement, and fiber reinforcement that is used as ingredient of concrete or mortar and is added to the batch immediately before or during its mixing. Okay, so that is added in fresh state. So before the concrete hardens, we add the chemical admixtures. We add admixtures. Okay, so within that we have mineral admixtures or cementitious materials such as flash, like we discussed last time, and we have this we're gonna discuss today, which is chemical admixtures. Okay. So chemical admixtures do not replace cement. So this is one of the major difference from mineral admixtures. So for mineral admixtures, for example, flash typically replace 10, 20, 30, or even more percentage of Portland cement. Okay, but for chemical admixtures, they do not replace cement. Okay, so they may have very great effect on fresh properties. They may increase the workability of a concrete, for example, or change the setting time, either increase the setting time or reduce the setting time. Okay. But this should not affect the mechanical property of concrete significantly. Right. So that means the strength of concrete should not be affected by chemical admixtures if the other mixed proportions does not change. Okay, that is also different from mineral admixtures. Okay, so when we replace Portland cement with 10% of silica film, the strength will go up quite a lot. Okay, but just add some chemical admixtures to the mix, the strength should not change too much. Okay, so chemical admixtures should have to improve the durability of concrete in the case of air entraining admixtures or corrosion inhibitors. Okay, so these are two types of chemical admixtures we will discuss. Okay. There are many different types of chemical admixtures, such as air entraining agent. So that's entrain small, tiny air bubbles in concrete to make the concrete more durable. Okay. We could have set controlling admixtures, okay, or water reducing agent, sometimes also called plasticizing admixtures. Okay. Or we could have corrosion inhibiting admixtures, reduce the corrosion of the steel reinforcement in concrete, reduce the shrinkage, we call that shrinkage reducing admixtures, or even change the viscosity of concrete. In that case, we call that viscosity modifying admixtures. Okay. So this table summarizes the beneficial effect of chemical admixtures on property of concrete. Okay. So for workability, we can use water reducing agent, plasticizer, or so-called super plasticizer. That is another name for high range water reducing agent. Okay. Air entraining agent can also help the workability of concrete. Okay. For set controlling purpose, we could have accelerating accelerator, which reduce the setting time by increase the chemical reaction in concrete, or we could have a set retarding agent which slow down the hydration time, okay, increase the setting time of concrete. Okay. For strengths, we could have water reducing admixtures. Okay. If we use water reducing agent in concrete to reduce the water cement ratio, then the strength of concrete could increase quite a lot. Okay. For durability purpose, we could have air entraining agent for the concrete to resist freeze thaw damage, sulfate attack, alkali reaction. Okay. Water reducing agent, corrosion inhibitor sometimes can also be used for durability purpose. Okay. And we have different type of standard from ASTM for different type of chemical admixtures. Okay. For example, for ASTM CEE688, that is for set controlling and water reducing agent. Okay. They have a different type depending on the function, or sometimes they have a combination of more than one functions. For example, type D is water reducing and retarding, which is increase the setting time of concrete. Okay. For type E is water reducing and accelerating, which is reduce the setting time of concrete. Then let's look at the first one we're gonna discuss. Air entraining agent. Okay. So air entraining agent is mainly used for freeze thaw damage, which means the freeze and thawing of the water in concrete. If not well controlled, freeze thaw damage can cause the concrete to crack. Okay.
Concrete in cold, wet climates undergoes many freeze-thaw cycles during the fall, winter, and spring. What happens during a freeze-thaw cycle? No matter how low the water-cement ratio, concrete is somewhat porous. Water is able to enter the spaces and freeze. When water freezes, it expands. When there is no room for this expansion, stresses develop inside the concrete. The concrete relieves these stresses by cracking. Over many freeze-thaw cycles, these stress cracks appear as surface cracks or scaling. For quality concrete in freeze-thaw areas, an air entraining admixture should be added to the mix. Entrained air provides millions of microscopic bubbles of stress relief when water freezes and expands. Air entrainment is what makes this weather-exposed Chicago driveway different from the floors not exposed to the weather in this multi-story building, and even this driveway in Florida, which isn't exposed to the many freeze-thaw cycles.
So, air entraining agent is mainly used to resist freeze-thaw damage, but it may also be beneficial to resist other chemical or physical attacks such as alkali reaction and sulfate attack. Okay. Then let's look at how air entraining agent works. Right. So we know when water freezes, when water becomes ice, the volume will increase by about 9%. Okay. So that increase in volume need to find some empty space so the stress could be released. If that's not the case, the concrete may be cracked. Okay, so when we introduce these tiny air bubbles, which shows here in these green circles, okay, so this air is empty inside, and we have waters in capillary pores. The capillary pores is shown in these blue circles. Okay, so when water freezes, the increased 9% in volume will try to find some space. For example, these air bubbles. If that happens, the stress will be released, so concrete will not crack. Okay, so that's how air entraining agent works to reduce the freeze-thaw damage. when we reduce the water cement ratio, the concrete permeability will be lower. Okay, which means we have less amount of the capillary pores, and we also have less amount of water. So the freeze-thaw resistance of concrete will be higher. So when water becomes ice, the increase in volume will push either the ice or the remaining liquid. So sometimes not all the water become ice. So we have some remaining water in the system. So that will increase the hydraulic pressure in other places. When the increase in hydraulic pressure from this void, okay, ice will form inside this empty air, so stress is released. So that's good. As we can see from here, we can see ice formed inside this air voids. Okay, and this is cement paste. So we can also see from here, this is air inside cement paste after ice formation. After 5, 15, and 35 minutes, we can see clearly ice grows inside this air, so stress will be released. Okay. So air entraining agent typically made by organic matters such as salts of wood resins, petroleum acid, and so on. Okay. So that will create and stabilize small so-called microscope air. They can also stay in concrete for a long time. Okay. The dosage is very low, okay? 0.005 to 0.05% by weight of cement. So very, very small amount compared to flash and other mineral admixtures. Okay. So air entraining agent is the surface active molecule. So look at the molecule structures. It has hydrophilic, which means it likes water. The other end has hydrophobic, which means it hates water. Okay. Because the nature of this molecule, they will form air bubbles, and these air bubbles can be also stabilized inside cement paste. Okay. The figure on the right shows us how air content affect durability factor. Okay. So durability factor quantify how durable the concrete is to freeze-thaw damage. Okay. It is defined as, I'll show you in my iPad. Okay, oh. Can you see my let's see. Let me do it again. All right, so
it shows it loading.
Okay, how about now?
It's not. Oh, there it goes.
Okay.
I see the air in training.
Right, that's correct. Okay. So durability factor is defined as DF is for durability factors is P times N over 300. Okay. So P is the percentage of initial modulus of elasticity. That is one of the mechanical property of concrete. Initial dynamic modulus. Okay, so after N, N is the number of freeze-thaw cycles. So after N cycles. So what that means is after number of freeze-thaw cycles, we should see a reduction in modulus of elasticity of concrete. Okay, so that is the p-value, percentage of initial dynamic modulus of N freeze-thaw cycles. And N is the freeze-thaw cycles, and 300 is the number of freeze-thaw cycles. So the higher the durability factors, the closer the DF to 1, that means the smaller effect of freeze-thaw cycles on mechanical property of concrete. Okay, so closer to 1, the better. So from this figure, we can see the higher air content, durability factor will be higher. Okay, but this picture does not show the whole picture. When we increase the air content to higher percentage, then the durability factor will somehow be lower. We're going to discuss that in a moment. So here, the next slide shows us the typical one of the example structure, molecule structure of air entraining agent. Okay, so this molecule will form air, and this air can stabilize in the system, increase the resistance to freeze-thaw, and also make the concrete more workable, because this tiny air can serve as ball bearing due to its spherical shape. Okay, make the concrete easier to mix.
Is there a disadvantage of using that air entrainment?
Definitely. Very good questions, which we're gonna discuss right here in these slides. Okay, so spacing factor is defined as the average distance from any point in the cement paste to the edge of the nearest voice. Basically means the density of the air inside the concrete. Okay, these two figures shows us how the spacing factor affect the durability factor. Okay, so the bigger the space means we have less amount of air, it becomes less durable. However, if we increase air content too much, okay, the durability will go down. Okay, like you can see from here. The reason for that is because on one hand, more air we can release more stress due to the freezing of the water. On the other hand, because we introduce too much air, that will reduce the strength of concrete quite a lot. Okay. So that means we have a balance point, which is around somewhere 9 to 8%, which the concrete has the best balance between resistance to the tensile stress from the freezing of the ice, and also has the best strength, because the higher air content, the strength will go down almost linearly. Okay, so again, too much air, the strength of the concrete will be too low to resist the stress from freezing. That's why we have this optimal dosage for air, which is around 7 to 8%. Okay.
Are these admixtures like more expensive than the regular?
They
It makes a
definitely more
difference on the
expensive,
pricing?
but because it's just very small dosage, does not significantly increase the cost of the materials, not too much. Okay. So in the US, the majority of the cost from concreting is the labor cost. Okay, so the material is not too much, maybe 20-30% total cost. Yeah, the labor cost is the highest, and chemical admixtures take, I will say, less than 5 or 10% of the total material cost. So yeah, chemical admixture does not cost too much. Okay. Now here shows two mix with different percentage of aggregate, cement, and air. We care more about the air spacing, which is the ratio of amount of air to amount of cement. Okay, so that ratio is more important compared to the air percent by itself. Okay, so this two concrete has 8% air and the other one has 4% air. But air spacing, which is the ratio of air over cement, is more important correlated to the durability against freeze-thaw damage. Okay. And here we show some picture of the frost damage, or another name for freeze-thaw damage. Okay. When we have a joint, like here, the joint is easier to trap moisture and water, so we have more saturated concrete around the joint, and that's where we see more damage around the corner and the joint. Okay.
I work for the Illinois Department of Transportation.
Oh, really? Oh, okay.
I remember seeing like sometimes the scaling becomes so bad underneath the bridges that they have to put like boards underneath so pieces don't fall on the cars driving underneath.
Right. Yeah. Okay. Yeah. When I was graduate students, I worked for IDOT, the research project for IDOT, Illinois DOT, for SEC, self-constructing concrete, and some other project, for more than 5 years. So yeah, I've been to the field in Peoria, Urbana-Champaign area quite a lot. Okay. So yeah, glad to know also coming from. Yeah.
I was in Collinsville outside St. Louis. But yeah, I work on I-57 and those ones too.
Okay. Great to know. And this, it's called scaled concrete surface, which means the frost damage is only limited to the surface of concrete, as we can see from here. Only the surface. This is caused by the de-icing solution during the winter. Okay, so the icing solution is kind of salt. When we have snow on the road, we put that so the snow will melt, but that may also cause the concrete to this surface damage. We call that scaling damage. Okay, we're gonna talk about this more in the lectures of concrete durability. Okay. But today we talk about chemical admixtures. So air entraining agent can improve durability to resist freeze-thaw damage, to de-icing solution, to sulfate attack, which we discussed before, the formation of etching guy after concrete hardens. ASR, which is alkali silica reaction, is another type of chemical attacks in concrete. All of these physical and chemical attacks, they will generate a certain materials which is expensive, which means the volume will increase. Okay, so the tiny air bubbles can release this stress from the increase in volume. So that's how air entraining agent can help reduce these physical and chemical attacks. They may also improve the walkability because they behave like sand. The surface of air is smooth, circle size. So all of these will help reduce the friction between aggregate. Okay, so make the concrete more walkable. But the best thing about air entraining agent is it will reduce the stress. So for every 1% of air will cause 5% reduction in stress. So that's why we have the optimum dosage of air around 7 to 8%. Okay, too much air, the strength will be too low. It will also increase permeability, which means the air, not air, water and harmful chemicals such as chloride, the seawater can penetrate the concrete and do the damage more easily. So that's not good. Okay. Sometimes air entraining agent can also delay the setting time if overdose. Okay, change the setting time of concrete. That's all right. Here. The next one is set controlling admixtures. One is called retarder, which is increase the setting time. The other one is called accelerator, which is reduce the setting time. Okay. Let's look at the video.
To slow setting time and minimize cracking in hot weather, a retarding admixture should be added to the mix. In very cold weather, hydration and strength gain may slow or stop completely. To place concrete for this high rise in winter, an accelerating admixture may be needed to speed the concrete's set time and strength gain.
From early lectures, we talk about heat of hydration. Okay, so this is the 5-stage for hydration of C3S. Okay, we have rapid heat revolution, we have a dormant period. Okay, the dormant period is very, very important for us to understand the hydration process of cement, because during the second stage, the dormant period stage, there's not too much going on. The reason for that is because the system needs the concentration of the ions, such as calcium and hydroxide ions, to achieve a certain level. So we call that threshold concentration. So before the threshold concentration is reached, hydration product does not produce too much. Okay. So initial set time is the time when the concentration reach that threshold concentration. So we have more hydration product produced. So the concrete hardens. The hardens begin. All right. So for accelerator, we have two classes. The first one is called quick set. So that is for emergency repair. The concrete will set for in a few minutes. Okay. The chemicals such as sodium carbonate, the function of that is to increase the reaction speed of C3A. Okay. C3A is one of the compound which react the fastest. Okay. The hydration rate, number 1 is C3A, number 2 is C3S, okay, then C4AF and C2S. Okay, so quickset increase the hydration speed of C3A, so the concrete will set in only a few minutes. The second class is called regular accelerator. Okay, so that regular accelerator accelerates the reaction of C3S. So that means the induction period, which is the station 2 here, is shortened by increase the concentration of the ions. Okay. So concentration reach the threshold concentration with shorter time. So the reaction will be accelerated. It will also increase hydration rate in stage 3 and 4, which is here and here. Okay. So we use regular accelerators in winter concreting. That can ensure the concrete will not be too cold to freeze. Okay. Calcium chloride or calcium nitrate. So these calcium salts are normally used. Okay. The reason for that is when we introduce calcium salt from outside of the concrete, the concentration of the calcium will increase rapidly. Okay, so the calcium concentration does not need the cement to be dissolved by the water. So because we add calcium from this accelerator, so the time to achieve this threshold concentration is much faster. So that's how this chemical work. All right. The types of accelerator including inorganic and organic, but all of these are calcium salts, calcium salt, calcium formate, calcium aluminate cement, okay, because of the reason we just discussed. They can accelerate the rate of hydration, reduce the setting time, can also increase the early age strength. Okay. Calcium chloride accelerator does not use too much nowadays because chloride ions can make the reinforcement which is made by steel corrode. So chloride will make steel reinforcement rust, so cannot be used in reinforced concrete anymore. They may also increase the drying shrinkage, make the concrete to crack easily. So calcium chloride does not really need use too much, especially for reinforced concrete. But this figure shows us how calcium chloride can change the setting time. This is the increased dosage of calcium chloride. The initial setting time and the final set time, both reduce. And here's another example. This is the percentage of 28-day strength as a function of percentage of calcium chloride. Okay, at different temperature. Okay, so we can see when we add calcium chloride, the early age strength, 1 day, 3 day, 7 up to 28 days actually increase. Okay, so again, the major benefit of accelerator is to increase the early age strength. So the typical application of accelerator, we can use it to expedite the start of finishing operation, okay, reduce the time required to cure the concrete, increase the rate of early strength. So we can remove the formwork earlier, okay, save the time and labor, and early opening for construction for service, and so on. For retarder, that's the opposite of accelerator. So that can slow down the hydration process. Okay. Because of that, they can reduce the temperature inside the concrete. So for summer concreting, we may want to use retarder to lower the temperature. And also for mass construction, if the high temperature is a concern. Can also use to extend the concrete workable time. For example, if the concrete truck is stuck in the traffic, we can use some retarder to increase the setting time. Okay, it may also increase workability a little bit. So retarder works by slow down the C3S reaction by increase the second stage, by increase the induction period. Okay, so how that works? So the retarder is organic materials. They will form a coating around C3S particles. So the release of the ions will be slowed down because of this coating. Okay. Organic retarders also absorb on nuclear of calcium hydroxide. So it will also slow down the growth of calcium hydroxide. It will also slow down the C3A reaction by absorbing into C3A hydration, which is ethylene dye and monosulfide aluminate. Okay, so they work on all these three compounds in concrete. And here shows us example. Some people test, see how delayed addition of retarder can change the final setting time. Okay. So delayed addition of retarder increase the effectiveness of retarder. Okay. Because less retarder is removed from solution by hydration production of C3A. So let's look at these figures. So the figure, the x-axis shows us the delay time, which means how many minutes we delay after we mix the raw materials. We mix the cement with aggregate and with water. Okay. For example, here, this is 10 minutes delay of retarders. Okay. The final setting time will be much higher compared to 0 minutes delay. Okay. Why this only 10 minutes delay will increase setting time by that much? Okay. The reason just showed here. Okay. So initially we mix water with cement. We have a lot of going on from hydration of C3A because C3A reacts super fast. Okay. So we do not add retarders at the beginning. So we let the C3A to react. So, but after 10 minutes, we add retarder. So that will make retarder more available to work on C3S hydration. Okay, so that's why only 10 minutes delay, we have much more effectiveness on the final setting time. So most
I remember seeing. Oh, sorry. I remember seeing. So sometimes the trucks, when they came into the job site, that's where they add the retarder, right?
Yeah, sometimes in the traffic, when you want more time to work on the concrete, you add retarder. So the driver for the concrete truck, they have retarder, by their side. Just make sure if necessary they can increase the setting time.
Yeah, I never thought about this. So that's the reason they don't put it at the plant. They put it when they arrive on site. Or
Yeah, otherwise the concrete will set in the truck. Gonna be a disaster. Yeah. Thank you. So most retarders are organic materials, as we can see here: lignosulfonic acid, hydroxycarboxylic acid, and salt, or even table sugar or carbonated beverage. Regular Coke or Pepsi can be used as retarder, but not Diet Coke. Okay. We use retarder in cases such as traffic delay. If the temperature is too high, we may slow down the hydration, or we have difficulties place the concrete, we need extra time. Okay. Or we try to control the setting of large structure unit, trying to eliminate so-called cold joint. Okay. So cold joint means when we have very large formwork, we have one truck of concrete only can fill a certain part of that formwork. We do not want the first truck concrete set before we pour the second truck. If that's the case, we call that cold joint. So we want concrete to set as one big chunk. Okay. So in that case, we may also increase the setting time of concrete. Or for special finishing process, increase the setting time. All right. So that's the retarder. The next one is water reducing agent, superplasticizer. So these materials can make the concrete more workable, or if we do not change the workability, we can reduce the water cement ratio. Okay, so in that way we can increase the strength of concrete. So let's look at water reducing agent.
Chemical admixtures give concrete properties it normally wouldn't have. To make a mix more fluid, a water reducer can be added. Water reducers make the concrete flow easier from the pump, through the hose, to this elevated slab in this warehouse, without increasing the water content. If a water reducer is not used, pump hoses can become clogged and blocked, delaying the placement of concrete. Water reducers are also used for concrete in areas that are difficult to place, such as around congested reinforcing steel.
So water reducing agent has basically two functions. So one is to reduce the water content. So in that case, if we do not want to increase workability, so we want to keep the slump as the same, so we can reduce the water content by certain percentage. Okay, so in that way we can increase the strength of concrete. Or when we use to increase the workability and keep the same water to cement ratio, so basically means we do not change the water cement ratio, but by adding these chemicals we increase the slump. In that case we call that plasticizer. Okay. Most the water reducing agent are organic matters, as we can see from here. How this water reducing agent works. So this is show one of the functions of them. The molecule of the water reducing agent can neutralize the surface charge of cement particles. Okay, we can see here, before we adding water reducing agent, the surface charge of cement particles could be positive or negative. And positive or negative charge, they will attract to each other. So water reducing agent will neutralize the surface charge, make them all negative charge. So they will repel each other. So that's one function why it can reduce the water requirement. Okay. So here shows some of the example of the molecule structure of water reducing agent. Okay. Again, most of them are organic matter. We also have a so-called high-range water reducer. So they can reduce the water content by 12 to 30%. Okay. For high-strength concrete or self-consolidating concrete, if we want very high strength by lower the water to cement ratio, or we want to increase the slump to extreme extent, then we want to use superplasticizer. Okay. Typically 1 to 3% by weight of cement. We have different type of superplasticizer. Again, they are all polymeric materials, such as this is called sulfonated monoamide formaldehyde, or SMF. Another one is SNF. The newest one is called CEE type, or polycarboxylated type. Okay, so very hard to pronounce, but this one, the CE type, is the newest type superplasticizer. So one of the function of water reducing agent is working by neutralize the surface charge. But there's another mode of action. One of them is called physical binding and dispersion. Okay. So here shows without water reducing agent, the cement particles is fluctuating together. But the water reducing agent, the molecule will wrap up around the cement particles, so make the friction between the particles less. so better dispersed in less water. So this is called physical binding and dispersion, so another mode of action. And this is the first one we just discussed. Two cement particles in these two gray squares. So neutralize the surface charge. So two particles has the same charge, so they repel each other. So we call that electrostatic repulsion. So that's the second mode of action. The third mode of action is called steric repulsion. This is due to the bulky nature of these organic molecules. The organic molecule has long arms, so they wrap around the particles, and this long arm will prevent the cement particle from stick to each other. Okay, so we call that steric repulsion. So water reducing agent can not only work on cement, but other type of mineral can also be well dispersed using these chemicals. Okay. As you can see from here, this is a type of mineral paste. This is when we add 10 more % of water, it becomes well dispersed. But this is 0.1% by weight of the paste. This one type of water reducing agent. We can see even more dispersion compared with 10% of more water. So water reducing agent is specified in ASTM C494. We have again many different types: low range, high range, and one or two functions. Type A is normal, low range. Type D is water reducing plus retarding, which means the setting time will be increased, or accelerating, reduce the setting time. So depending on what you want for your concrete, you can choose different type of water reducer. So we can use water reducer to either increase the consistency. Consistency means how easy the concrete can flow. Okay, increase the slump. Or we can use it to achieve higher strength by reduce the water to cement ratio. Okay, we can also use it to reduce how much cement used in concrete, because we can use less cement to maintain the same slump. So save the cement, save the cost, and save the environment. Okay. But not all these three benefits can be obtained at the same time. We can either increase the slump or increase the strength, reduce the cement, but typically cannot get all the three benefits at the same time. Okay, like we can see from here, the options for water reducing applications. Okay. If we keep the water content, this is the X cell is the water content, the Y cell is the slump flow, the flow. Okay. So we keep the water content constant. When we add superplasticizer, the workability will be higher. Okay. But if we keep the slump constant, like in these errors, we can reduce amount of water. So we use lower water cement ratio, the strength will be higher. We can also use less amount of cement. Okay. This figure compare concrete with different type of superplasticizer. So C is for control, I believe, which is the red line, which means has no superplasticizer. N, M, and X are concrete with different type of superplasticizer. So basically, we can see the strength does not change significantly depending on the what type of superplasticizer we use. Okay, so that means we do not change the water cement ratio. Okay, so keep that in mind. But if we using this to reduce the water cement ratio, we're gonna see a lot of increase in strength. Okay. So beside reducing the water cement ratio, a well dispersed and more homogeneous concrete can actually improve the cement efficiency, reduce the entrapped air, which is in the big air bubbles in concrete, which can significantly reduce the strength. So that function itself can kind of increase the strength up to 25%. So do not change the water cement ratio. By adding these chemicals, we can make the concrete more homogeneous, so that can make the concrete has higher strength. Remember, superplasticizer is essential. It's a must for high strength concrete. All right, so that's the major type of chemicals we discussed. Corrosion inhibitors, by its name, we know it can reduce the corrosion potential for reinforced, which is a steel rebar. We have different type depending on how it works. Anodic inhibitor, cathodic inhibitor, and mixed inhibitor. We'll talk about this more when we talk about corrosion of concrete, which in one of the lecture of concrete durability lecture. So corrosion inhibitor can control the corrosion of steel reinforcement, and the dosage depending on how much chloride level you anticipated from the concrete. Okay. For example, if the concrete will be exposed to the seawater, you will expect more chloride concentration in the concrete. Okay. Here shows different type of corrosion inhibitors, example of chemicals, typical dosage, and how they will work on the concrete. Okay. The last one we're going to discuss today is shrinkage reducing admixture. Shrinkage is a very important potential problem for concrete, and we have a lecture on shrinkage itself. Okay. So shrinkage reducing admixtures, by its name, we can reduce amount of shrinkage. Okay. So it's working by reducing the surface tension of the pore solution. Okay, the pore solution means the water inside the concrete. Okay, again, we're gonna talk about this more when we talk shrinkage of concrete. Okay, but today we know we have some chemicals which can help to reduce the dry shrinkage of concrete. So they are shrinkage reducing admixture. All right. So today we discuss several types of chemical admixtures. We should know what's the difference between chemical and mineral admixtures, and how, for example, water reducing agent work, how set controlling admixtures work, air entraining agent work. Okay. So that's the end for today's lecture.